Thanks everyone for coming. It's been 2 days of exciting talks and discussions. Today's our last day and the talks will be centered around gravity, although there will also be talks about interferometry and AMO methods. And our first speaker, will be Hartmut Grote, who will tell us about quantum-enhanced interferometry for new physics. So please take it away. Ms. Hartmut.
Yes, hello everyone. Yeah, thanks for this interesting conference and for the opportunity to speak. Before I start, I would like to mention that for those of you who know the Quantum Technologies program in the US, we have a similar program in the UK, which was actually inspired by the US model. And so I'm talking about the work mostly today, but not only of one of these funded consortia. So we have been funded for quantum enhanced interferometry for new physics. That means for experiments trying to discover new physics, of course. So we are a consortium of 5 UK universities and international partners. And just to mention, some of the other consortia funded are working, for example, on the topics that already have been covered, like, for example, the UK atom interferometer. ION is one of the consortia, and an atomic clock network, for example. Okay, so we are working on 2 themes, the nature of dark matter and the nature of space-time, using interferometry. And to start with the first theme, the nature of dark matter, which is of course a very large topic, I found this diagram which is supposed to be a pie chart that is from the 90s, from the cosmologist Michael Turner. And so that's his landscape of possible dark matter candidates at the time. And so you see there are quite large area axions and neutralino, which is a WIMP particle. And so at the time, it seems axions, at least in his mind, were already a viable candidate. But as history went, of course, as you know, there was a larger focus in experiments on the very promising WIMP dark matter candidates. And so our first 2 experiments, we have overall 4 experiments that we are doing or supporting. And the first one is a search for axions as a possible dark matter candidate in the galactic halo. So these are not the axions that directly would solve the CP problem, which, as you know, originally motivated the axions. But if you decouple the coupling constant from the mass, then you have a whole landscape which is more or less motivated, but there's a range of experiments searching for these. And so one of the famous ones, for example, is ADMX, which is actually looking for the CP axion. But we are building a new tabletop experiment that searched for the axions in the galactic halo. So if you will, this is an interferometry haloscope. And the second experiment is a so-called light shining through wall experiment in which you generate the axions in the experiments and also detect them there. So the dark matter question there is only secondary, if you will. It's a new particle search. So axions, yeah, pretty much behave classically as a field because their mass is so low that you have very large occupation numbers, and so they are well described as a field, as we have heard before. And it was only a few years ago pointed out that in fact they induce a phase difference between left and right polarized light, and that does not need an external magnetic field. So it relies on the self-interaction of the axion with the light field. So whereas ADMX, for example, as you know, uses an external magnetic field to convert axions to photons, it's possible to see this polarization rotation effect just on a laser beam in the galactic halo. So with the hypothesis, of course, that the galactic halo is composed of axion dark matter. And so this has further developed in a series of papers. It was originally proposed maybe for implementation in a gravitational wave detector. But now it's realized that it's probably better to do this as a separate experiment. So what we are building in our consortium is a tabletop which essentially consists of a ring cavity. So you have a laser that is resonant in this ring cavity, and then due to an axion-induced rotation of polarization, effectively you get some side bands at an offset frequency, which in a ring frequency, which in a ring cavity then resonate at slightly different frequency. And there's a tuning cavity attached to this, where you can couple out the other polarization, so the signal field, and resonantly enhance this as well. And so you can tune the whole setup for different axion masses. And further, then the sensitivity is increased with the application of squeezed light. Okay, if you just look at the red solid graph here, this is a possible exclusion plot for our tabletop setup in a mass range down to 10 to minus 16, perhaps. Here's ADMX for comparison. So this solid line is what we potentially can reach, but the technology should be possible to scale up to larger setups. So if you scale it up for 4 kilometers, for example, you could get down here. And I'm not a theorist, but I just learned recently that there are also some new models predicting axion-like particles possibly in this mass range, which could be reached here. Okay, and our second experiment is a support to a larger experiment. So that's the so-called light shining through a wall experiment. So I have mentioned ADMX, which uses this Primakov process on the upper right Feynman diagram here. So you have an axion field that's in the case of RDMX, that supposedly is dark matter, and that interacts with a static magnetic field and generates photons, which you try to find. But as I mentioned, you can also try to generate axions with the inverse process and detect them in the very same experiment. And so you have a wall here in between, and then left and right side of the experiment. So on the left side here, we have a strong pump beam and electromagnetic wave, a laser wave. Then we have an external magnetic field, and this generates axions. The axion travel an optical barrier, which the photons cannot pass, and then are reconverted. So you do conversion and detection in the same experiment. That's a light shining through a wall experiment. And there have already been a few of them that have published early results. What is currently under construction at DESI in Germany, in Hamburg, is the ALPS 2 experiment. So this is a photograph of the installation of the magnets, which has just been finished. So this is 2 120-meter beam lines. So it's really a linear setup folded into one photograph. We are looking at the central area here, which contains this wall. So on the left-hand side, we have the 120-meter string generating axions. On the right-hand side, we try to detect this. And particular, what we are focusing as an improvement in the UK is, for example, to make a better single photon detector. So one of the methods to then search for axions is to look for individual photons. So in principle, as I said, this right-hand side should be completely dark. And so you can look for individual photons on as small as you can get background noise. And so that is done. One method to do this is with a transition edge sensor at cryogenic temperatures. So here's another sketch of this, what we call the production cavity. We have a standing wave of 150 kilowatts there. So these are optical cavities that enhance the ingoing light. And what is new for this setup is there's also a resonant cavity on the right-hand side. And so the difficulty of this experiment is really to keep the right-hand side cavity also on resonance for the axion field, so on the same optical frequency on the left as on the left-hand side. And so this is done with some auxiliary laser fields, but is part of the difficulty. And yeah, as I said, this is under construction now, and here are some details for those of you who may be familiar with test detectors. So we are working on some innovative test detector with very low dark count rate, 10⁻⁶ per second perhaps. And we also have some ideas how to include a second detector on the device as a cosmic particle veto, and so on. And so supposedly we can improve the background noise with this test detector. Okay, and this is these blue lines in the exclusion landscape is what ALPS can reach. You can compare this to CAST, for example, which is another type of search for axions, which searches for axions that are generated in the sun. So it's a tube pointed to the sun with a large magnetic field, where then axions from the sun can reconvert into photons. And there are also some ideas, let's say, how this could be scaled up. So the light shining through a wall experiment on a kilometer scale. So we are now at 120 meter scale, and of course people think here also about kilometer scale. But the scaling is it's very difficult to get substantially further. So maybe we need some new technologies there as well. Okay, so speaking of kilometer size extensions, I want to make a small excursion here, a side remark on gravitational wave detectors. So one of the ideas is indeed that maybe when third generation gravitational wave detectors come online, at some point these facilities that you know, LIGO, Virgo, and also maybe Kagra at some point may become obsolete for the detection of gravitational waves. So that's really 20, 30 years down the line. But then these facilities maybe could be used for other fundamental physics experiments. So this axion search type haloscope might be one idea. I just wanted to remark, because we use interferometry for fundamental physics, I wanted to make a remark on the sensitivity of these instruments. Already Holger Müller mentioned yesterday the remarkable sensitivity of interferometry. So if we compare what we achieved today with Michelson's interferometer from the late 1800s, so here the sensitivity of 10⁻⁹ relative, roughly, and today we have 14 orders of magnitude more sensitivity, mostly because of some optical enhancements of the basic Michelson schemes. You can see the basic Michelson scheme that you know here on the left side, beam splitter and two end mirrors. In the modern gravitational wave detectors, this is enhanced with optical resonators in the arms and so-called power recycling. All of these you can simply think of just they increase the laser power, and so they reduce the quantum noise. One of the quantum noise sources is the photon counting noise. So today they achieved about 400 kilowatts of light in the arms. And then since a few years, we also have squeezed vacuum techniques. So all of the large gravitational wave detectors now used a source of squeezed vacuum, non-classical light to reduce the quantum noise. So this is injected from the rear end of the interferometer and lowers the quantum noise. So that is a remarkable sensitivity today of 10 to minus 19, 10 to minus 20 meters, which is 10 to minus 5 of a proton size, which of course is only possible by averaging over a pretty large area on the surface of a mirror. But that naturally begs the question, how can this be used for other fundamental physics questions? So just to point out that soon the Heisenberg uncertainty limit of these 40 kilogram test masses will be reached. So the measurement then is so precise that in one moment, if we take one measurement, the test masses get a kick, which makes the next measurement a bit more imprecise. So there are techniques to counteract that with so-called frequency-dependent squeezing. So of course you cannot go around the Heisenberg uncertainty, but you can modify this squeezed vacuum in a way that you can go below the standard quantum limit. Okay, and another interesting connection is of course potentially between dark matter and gravitational waves. And I found this mind map interesting from a paper on the archive. You can see here there are all sorts of, or could be all sorts of connections between gravitational wave and dark matter. Dark matter is of course not the only topic for fundamental physics, but we can explore what is already being explored. For example, this red part on the right-hand side, so-called environmental effects, which come from dark matter around binary black holes, for example, which may affect the total merger rate, which may lead to slight waveform dephasing in the late phase of spirals, and also which can lead to quasi-continuous wave if you have by the super radiance effect around black holes. And in particular, this one, the last one already has been searched for. I want to point out here another branch, which are the direct searches for dark matter with interferometers. And so in this case, we use the very sensitive gravitational wave detectors directly as dark matter detector and not mediated by gravitational waves. And there are some examples, because there's not so much time, I'll just mention in more detail one, but there has been already publications for LIGO dark photon search and some other ideas. We recently have been working on so-called scalar field dark matter for the GEO detector. This is a small prototype gravitational wave detector of 600 meter long arms in Germany, which is particularly suited for the scalar field dark matter search because it does not have these arm cavities you see in LIGO. And so the effect is quite simple to understand. As was mentioned in one of the earlier talks, the scalar field dark matter can lead to a variation of fundamental constants. And this happens at the frequency of the scalar field. And so this variation of fundamental constants, in fact, makes all objects oscillate in size at this frequency. And so the argument for a long time was, in a gravitational wave detector, this cancels to first order because the end test masses both get bigger and smaller at the same time, then this effect cancels. However, there is a symmetry in each interferometer, or at least if you set up the beam splitter in a certain way. So in these interferometers, the beam splitter is a piece of glass a few centimeters thick, and you have this beam splitting surface here. And so as this beam splitter oscillates in thickness, then this reflection surface goes back and forth. And this, in effect, makes a net differential effect in the interferometer, which you can use to search for scalar field dark matter. So we recently completed such a search with data from the GO600 detector, and we could set these green shaded new upper limits. So we didn't find any surviving candidate for dark matter, but it's quite interesting that even with this first search, we can set some interesting new upper limits. And yeah, there's of course more to be expected in the future, especially if you make some small design changes to the gravitational wave detector. You can significantly enhance this sensitivity and still search for gravitational waves at the same time. Okay, and that brings me back to the last two topics, how we use quantum enhanced interferometry. So quantum aspects of space-time. We have two experiments there. So we call it experiment 3 that searches for quantization of space-time, and another one that looks for signs of semi-classical gravity. Okay, quantization of space-time is hypothetical, of course. Maybe most physicists assume that there is some sort of quantization of space-time, but of course nobody knows. And maybe it could happen at the Planck scale at 10 to minus 35 meters, but also that's also not known. But if so, then there is of course not much chance with current or foreseeable technology to reach this scale directly with experiments. However, in combination with the holographic principle, this may be possible. So this is quite speculative, high risk, high gain research, and the theory is still under development. But the holographic principle, in a nutshell, is the statement that you can only put as much information into a volume than fits on its surface. And so that leads to some reduction of information density, and as a consequence, probably to some correlation or an entanglement between different regions of space-time in terms of their information content. And so the idea is to probe this with interferometers, with two independent interferometers, which are closely located, and then you search for correlated noise between the two interferometers, where in standard physics there should be none. Okay, and there has been one experiment already in the US which went forward with this idea first, the so-called holometer experiment at Fermilab, which are two co-located 40-meter power-cycled Michelson interferometers, and they set a few upper limits for some configurations. There's an instrument description as well. And so we are taking this idea forward to lab scale now. So this time we are not scaling up, we are making it smaller, and mostly to be more versatile. So there are more, even though the Fermilab holometer has set interesting upper limits, there are more geometries to test. So we want to build a tabletop interferometer which is more easy to maintain and reconfigure, such that we can also test 3D geometries, for example. So in the future, maybe we would bend one of these arms in the middle upwards, and then there are certain combinations of geometry that lead to different, or may lead to different predictions of noise. And at the same time, a tabletop setup allows us to be more flexible with the technology as well. So we are planning to have a higher sensitivity, though the arm length is shorter, but with some improved technology as time goes on. So we plan to have 10 kilowatts in these tabletop interferometers, for example. Output mode cleaners are added. That means very fast data acquisition system, and we'll also add squeezed light, with the Fermilab holometer did not have. As a side remark, there also is a proposal of using so-called entangled squeeze states. So if you cross the squeezing beams here, you can have, in principle, some achievement if you look for correlated noise between the two interferometers. However, this relies on extremely low losses, so it's not so clear yet whether that is really beneficial. But it's an interesting idea to investigate. So here's our planned sensitivity. There's a paper also that describes this tabletop setup. So the red trace here is the displacement sensitivity in meters per square root of Hertz achieved by the Fermilab kilometer interferometers 2 times 10 to minus 18 meters per square root of Hertz, up to from 1 to 25 megahertz. And so we hope we can be up to 10 times better in displacement sensitivity with increased power and with the use of squeezing. Again, here it's interesting to note that if you build a very sensitive interferometer almost as a byproduct, it can also be again sensitive to these other questions as dark matter. So again, this will be sensitive at some level to scalar field dark matter. It's a bit less compelling at these higher frequencies, but still it will be possible to set new upper limits in this mass range of up to 200 megahertz. And at the same time, it's also a very high frequency gravitational wave detector. So the gravitational waves above the LIGO-Virgo band, above 10 kilohertz, are not so well researched yet. However, there is a recent sort of white paper of some ideas. There are certainly some possible sources from the Big Bang or primordial black holes, and even transient signals maybe in certain multidimensional theories. So there are some ideas, and so as gravitational waves are proving so valuable for fundamental physics, it's certainly worthwhile, we think, also to, in principle, to think about how to detect gravitational waves at higher frequencies. So interferometry is not necessarily the best technology to do this because of the length scaling, but it will still be possible to set new upper limits with this setup as well. Okay, and I'll briefly mention our fourth experiment. That is an experiment with cryogenic cavities that tries to find signatures of semi-classical gravity. So in semi-classical gravity, the gravity is not quantized, but matter is treated as quantized. And so you can look for self-interaction of the mirrors in a cryogenic cavity. And then depending on the theory, you get a frequency splitting or not. And also related to that theme, there's a recent new idea from 2 of our members of the consortium for another tabletop setup. So if you will, all these last 2 experiments are also quantum gravity tabletop setups in a wider sense that look at least at some aspect of quantum gravity or quantized space-time. And so here the idea is that you bring 2 masses close together which interact gravitationally, and then instead of trying to detect the entanglement between them, you look at the effect on this entanglement has on the light in forms of squeezing of the light. And so this may make this accessible to a test as well, which is described in this quite new paper with some parameters here. So it's quite challenging, but not totally unfeasible. So you need 10 millikelvin. You have to detect at 10 hertz, very high Q materials and high density matter. Okay, and I'm almost at the end. This is just to mention that we also have funding in our consortium for new coating facilities. So pretty much all of our experiments rely on ultra high performance optical coatings, and so there's a new technology, ECR ion beam deposition, in development, which we can make use of in our consortium, and then of course it's also useful for the wider community. Okay, these are our international partners, and that brings me to a summary, if you will. So as I pointed out, the interferometry has been very nicely perfected for the purpose of detecting gravitational waves. And we do already fundamental physics with gravitational waves, not only dark matter, but for example, the realization that gravitational waves travel pretty much as the speed of light came out of the binary neutron star detections and several others. And it's also possible to do direct dark matter searches, as I pointed out, with gravitational wave detectors, scalar fields or dark photons, possibly others. But of course, we can also then more tailor interferometry to other questions of fundamental physics experiments. And so I showed you the examples of a new type of axion search with interferometry for a haloscope. I explained the light shining through a wall experiment, ALPS, and then we have this quantization of space-time experiment and the semi-classical gravity. Okay, thank you.
Okay, so thank you very much for the very nice talk, and we'll open it up for discussion for about 15 minutes. Any questions from the audience, you can put up your hand and let's see. Yeah, so Tanya Rusi, go ahead.
Hi, thanks for a great talk. I was wondering about the Axion search with the interferometry haloscope. Can you talk a little bit about what your scan rate might be like?
Yeah, I think these plots are made for something like 1 year of integration, if I recall correctly. So, I mean, in principle, you use ideally you scan as long as corresponds to the coherence time. So we expect that the coherence time is of the order of 10 to minus 6 of the frequency, or the inverse of that. And so, yeah, there's a kind of a natural time which you integrate, but this composed sensitivity here is about a year of work, order of magnitude, I think.
I guess I don't understand that. There must be something I'm missing. So the reason ADMX's exclusion is so narrow is because you can't physically change the width of the cavity fast enough. So is it just the fact that your axion mass is so much lower that you don't need to spend very much time at each cavity length?
Yeah, and you can also you have much more freedom with this coupled cavity to change the resonance frequencies.
Got it. Thanks.
Mariana?
Thank you for a great talk. Can you talk a bit more about the experiments for semi-classical gravity? I didn't understand what specific new physics you're looking for there. Can you clarify a bit more?
Yeah, maybe it's more productive if one of the authors speaks to that. I think Animesh, would you take this on?
Yeah, sure.
Animesh, we can't hear you.
This one or the next one? This one. Yes, I can talk about this one. Is this the one you're doing, Mariana?
Yep.
Well, so here what we are looking for is the consequence of gravitational interaction. So if gravity is linearized gravity at low energies follows a Newtonian form versus if it follows some sort of semi-classical form like Newton. And what the basic sort of fact is that Newtonian gravity depends only on the relative position of the two masses. So if you think of the interaction between the masses A and B in their common and differential mode, the effect of the gravity is only in the differential mode. But that is not true for the Schrodinger-Newton type model, where the effect of that gravity appears both in the common and the differential mode. So that is basically what we are proposing to detect as a way of either verifying one or ruling out the other.
Okay, thanks so much.
Yeah, can you actually elaborate a little bit more on that? What is Schrodinger-Newton gravity?
So this is one of these semi-classical models of gravity where the matter is treated quantum mechanically, but the space-time only responds to the averaged, sort of the expectation value of the masses, not in a quantum sense, but in a classical sense, that it's the expectation values of those tensors that affect the space-time.
So basically, in Einstein's equations, on the right-hand side, you substitute in the expectation value of some quantum energy momentum tensor?
Yeah.
Okay.
Yeah, I mean, I must point out that this is sort of one of the numerous umpteen candidates, but I think it is already known that it has other issues like not being Lorentz invariant and allowing superluminal communication and such things. But I don't know, there may be other people who are sort of greater experts on Schrodinger-Newton models than I am. In the audience, I mean.
Some years ago, there was a partially tongue-in-cheek experiment done by Don Page and I think it was his student Gilker, testing that semi-classical Einstein equation and showing that it's not valid. Is there a conceptual problem with that experiment, or does it not test the same thing that you're talking about trying to test here? I think they used a Geiger counter to determine the placement of masses and then did the statistics of that experiment. Looked at the statistics.
Yes, I don't know if you're referring to the sort of the 1980s Page Gleicher experiment.
Yes.
Yeah, so that I think, yeah, it fell foul for various reasons, one of which was it sort of relied on a specific interpretation of quantum mechanics, this many worlds interpretation and so on, and seemed not to be very transparent in other sort of interpretations of quantum mechanics. So if you go look at the original paper in PRL, there were sort of comments to the editor and so on and so forth that sort of argued on this kind of topic. But I don't know if this specifically addressed Schrodinger-Newton, I must.
Yeah, I mean, would the same arguments not apply to, why do they not also apply to this experiment? I guess that's the question. What's the key difference between this and Page and Gilker?
I don't think they were saying that there was a difference in the common and the differential modes of the motion of the masses, if I remember correctly.
Okay, Katie?
No, it's just trying to follow, this discussion because I still wonder, whether it. I mean, Animesh, you mentioned that this Lorentz invariance, but if it isn't about kind of slow-moving bodies where kind of Newton approximation does work, right? Then then it's just quantum mechanics. So in this way, this kind of Lorentz invariance for the linearized gravity, I wonder how it enters if it's kind of just slow moving objects where you can use just a normal quantum mechanic. I mean, not checking Lorentz invariance, but I might be wrong about this. So at which point this relativistic effect enters into the play?
Oh no. So in what we are proposing in the slide you see on the screen,
yeah,
has nothing to do with relativistic masses or Lorentz invariance. That was a comment I made.
I see.
About the theoretical analysis of the Schrodinger-Newton model.
Yeah. So it's like, you know, kind of a bending of light, right? There, when you have bending of light, you are using, relativistic nature of the light, right? So you are saying that in this experiment, this also enters. Did I get it right?
No. In this experiment, there is nothing to do with the relativistic nature. The masses are, I mean, they are, as I said, linearized, basically very slowly moving, and yeah. So no. So this experiment does not test Lorentz invariance or any such thing.
I see, but then to me it sounds like a normal quantum mechanic, because in this way it's instantaneous interaction, and in this way locality of the theory at short distance, whatever, does not enter. You know, because you can say that it's just kind of long range instantaneous interaction. I mean, no,
I think. No, I think you are correct. I think we are back to the discussion we were having yesterday.
Right.
Towards the end. What exactly are we testing in these experiments? I think that is a valid question.
I see. No, I was wondering whether it's a different perspective in this case. No, you're saying that it's more or less the same, right? I see.
No, I mean, yeah, so my present state of understanding, as we show in this sort of, it's a fair, as I said, the basic fact is that the gravity acts only in the differential mode and not in the common mode. So the only effect, the observable effect, is a shift in the oscillation frequency of the common, of the differential mode with respect to the common mode. So it has, so I do not know to what extent you will interpret that. I mean, that has nothing to do with quantum mechanics per se, right? I mean,
I see.
Yeah, so,
yeah, I understand. Okay, thank you.
So, Mariana, did you have another question?
Oh, no, sir.
Okay, and Igor, you also had your hand up, but you don't anymore, so did you have anything?
Right, thanks. Well, I just had a quick comment because of the question about the Page-Geiger experiment on Schrodinger Newton, but I think Animesh said it precisely right. There's this crucial additional assumption that you have this kind of many worlds interpretation. So it's a classical experiment actually, but with this additional assumption, you assume that you branch off all the time in all different possibilities, and then you take the average of them. So even then classical experiments would give you some signature. So it is a tongue-in-cheek experiment, like said, but it is under this additional assumption. So I think it's very valid to also probe it in the kind of quantum realm. So it's two different things, this experiment and the Page-Geiger.
Yeah, thanks, Igor.
Helmut, so I was also intrigued when you mentioned experimentalists were sort of preparing experiments for having to do with holography. And you said that the theory was in development, but I was wondering, like, what are the specific kinds of things that, experimentalists are thinking about testing in relation to holography? Because
yeah, essentially what we are looking for here is correlated noise between two close by interferometers, so which share some part of the space-time region. And so yeah, I mean, I can only say it as I said before. Maybe the holography aspect or the holography idea here is that due to the reduction of information, so if the holographic principle holds, then there must be some reduction of information in three-dimensional space-time, for example. And so the consequence of that would be that the path length noise that the light accumulates when it travels in these arms, due to the space-time overlap of these two interferometers, should have some correlation, because the information in this volume cannot be completely independent. There cannot be a completely independent space-time quantization noise in each Planck volume, for example. And so depending on how you apply the holographic principle here, and I think that's an open question, So in that sense, it's quite speculative, but depending on how you apply it, you could maybe see correlations between this. So there's a little bit of theory work from Craig Hogan, but more lately also from Katrin Zurek and Eric Verlinde that look into these ideas. So it's certainly under development, but the idea is there is some correlation of noise due to information reduction, hypothetically.
I see.
Yeah, this is Doug. Let me sharpen up that question. Wilczek and collaborators have worked on this and find that the correlated fluctuations are only on the scale of the Planck length, independent of the length of the interferometer, and therefore, as you already said, unobservable. However, Verlinde and Zurek propose that the effect goes as the square root of the length of the apparatus, that is, the variance is add over length. Do you expect to distinguish between those two possibilities?
Yeah, I mean, I think Zurek and Verlinde are working right now on predicting a power spectral density. So this would be the equivalent of what we can see in the experiment. So we have to see where that gets us, whether we can rule that out or not. But in that sense, it's a proof of principle experiment that yeah, we have to see where that calculation ends up.
Okay, I think we have to move on to the next talk. Andrew, maybe we can take your question to the general discussion.